Welcome, and thank you for joining us on this custom-tailored deep dive. I'm your host.
And I'm the resident expert here to help untangle the tech.
We've built this specific exploration just for you, pulling together some truly groundbreaking research.
Yeah, to help you stay at the absolute cutting edge of where technology is actually heading right now.
Because today, our mission involves navigating a massive, paradigm-shifting new research paper, straight out of Google Research and Google DeepMind's.
A big one.
It really is. We are looking at a brand new artificial intelligence model called VaultGemma 1B.
Right.
And the core mission of our deep dive today is figuring out a puzzle that, honestly, the entire tech industry has been wrestling with for years.
Oh, absolutely.
How exactly can we build incredibly powerful artificial intelligence without sacrificing our personal privacy in the process?
I mean, it really is the bottleneck of our current technological era. We want these models to understand the intricacies of the world.
Right.
But the world is fundamentally made up of our data.
Yeah, exactly.
So finding a way to train an AI so that it learns the underlying patterns of human language.
Like how to write an email or...
Right, or how to code, how to summarize an article without actually memorizing the private, specific details of individual human lives. That is essentially the holy grail of this field.
The Holy Grail.
Yeah. And the source material we have today lays out a comprehensive, mathematically rigorous approach to doing exactly that.
Okay, let's unpack this. Because to understand why VaultGemma 1B is such a massive leap forward, we first have to talk about the bad habits of standard large language models.
The very bad habits.
Right. As you probably know, to get smart, these models consume massive amounts of the internet.
Trillions of words.
Trillions. From web documents, forums, code repositories. But because their entire architecture is built around just, well, predicting the next word over and over again, they develop a severe vulnerability.
Yeah, they have a bad habit of what researchers call verbatim memorization.
Which means they accidentally regurgitate sensitive data.
Exactly. Or personally identifiable information, PII, that they just happen to see during that massive training phase.
And the scale of that pre-training data is almost incomprehensible.
It is, which makes the memorization problem incredibly stubborn. I mean, even when developers employ really rigorous filtering efforts to scrub their data sets.
To get rid of unwanted or unsafe utterances.
Right. The sheer heterogeneous volume of the internet means some sensitive information inevitably slips through the cracks.
It always does.
Yeah. And when a model memorizes that rogue data, a clever user can prompt the model in a highly specific way and actually extract that exact verbatim training data right back out.
Which is a terrifying thought.
Oh, for sure.
When you consider things like medical records, private internal corporate emails, or secure code snippets that might have accidentally ended up in a web scrape.
It's a huge liability.
So the industry obviously knows this is a problem, but the solutions up to this point haven't exactly been foolproof, have they?
Yeah.
Why are the current privacy solutions falling short?
Well, if we connect this to the bigger picture, the current industry standard is to apply something called differential privacy, or DP, only during the fine-tuning phase of an AI.
Okay, so just at the end.
Right. Fine-tuning happens after the foundational model has already been pre-trained on the wild, unfiltered internet corpus.
Got it.
Fine-tuning is really just a secondary, much smaller step. It's to teach the model how to behave politely or how to answer questions in a specific chat format.
Like a chatbot.
Exactly. So applying privacy only at this final superficial stage is fundamentally a flawed Band-Aid.
Because the damage is already done at that point.
Exactly.
The foundational model has already memorized all that massive pre-training data. Fine-tuning it later with privacy protocols doesn't retroactively erase the sensitive data it already swallowed.
Doesn't.
It feels a bit like, I don't know, building a house out of toxic radioactive materials, but painting the walls with lead-free paint and calling the whole house safe for your family.
That analogy hits the nail on the head. The underlying foundation remains completely compromised.
Wow.
And this practice creates a very dangerous false sense of security in the industry. Companies might slap a private label on a model simply because its final fine-tuning phase utilized privacy protocols.
All while leaving the core pre-training data entirely vulnerable to extraction attacks.
Exactly.
And reading through the research, this seems especially dangerous for what we call open weight models.
Oh, absolutely.
I mean, if a model is locked behind a corporate API, an attacker can only probe it indirectly, right? By asking it text questions.
Right.
But with open weight models, researchers and adversaries have full, unrestricted access to the actual mathematical weights of the model itself.
They can download it to their own machines?
Open it up, probe the architecture directly, and reconstruct the underlying sensitive information.
Yes. So if the goal is to have open, accessible AI for everyone, we absolutely cannot rely on a fine-tuning Band-Aid.
We need something better.
Which brings us to the core breakthrough of the research we're looking at today. The team at Google recognized that if you want true privacy in an open-weight model, you have to bake it into the foundation from the very first calculation.
So let's talk about the star of the show, VaultGemma 1B. I know from the paper that it's a 1 billion parameter model.
Yes.
And it was trained on a massive 13 trillion tokens, which is the exact same primarily English data mixture used for the standard Gemma 2 model.
That's right.
But how did they fundamentally change the recipe this time?
The crucial difference is that VaultGemma is trained with differential privacy from the ground up.
During that initial massive pre-training phase.
Exactly. And this isn't just a generic promise to try and keep your data safe. Differential privacy is a rigorous, highly specific mathematical framework.
Okay, so it's not just a filter.
Not at all. It guarantees, through mathematical proof, a strict limit on the influence of any single training example on the final model.
Meaning no one piece of data can shift the model too much.
Right. It ensures the model learns the general patterns of the crowd without being overly influenced by any single individual's specific voice or data.
So how do they actually pull that off mechanically? I mean, how do you feed an AI 13 trillion tokens of data and mathematically force it to not memorize any of them?
They utilize a technique called DPSGD.
Which stands for?
Differentially Private Stochastic Gradient Descent.
Okay, that is a mouthful.
It is. The team implemented this on top of their pre-training pipeline using a specific toolkit called JX Privacy. Now, the math can get incredibly dense.
Doesn't need all the equations.
Right. It essentially boils down to two key mechanics working together: clipping and noise.
I love this part of the paper. Let's break down clipping first because it's such a fascinating concept.
Sure. Imagine the training data as a massive stadium full of people, and everyone is shouting information at the model to teach it about the world.
A very loud stadium.
Very loud. And some voices in that crowd are naturally louder or more unique than others.
Like a weird piece of code?
Exactly. A highly specific, weird piece of code or a string of social security numbers. That acts like a very loud, unique voice.
Okay.
Those loud voices are the ones the model tends to latch onto and memorize.
So what does clipping do?
What vectorized, per example, clipping does is put a hard volume limit on every single person in the stadium.
Wow.
No matter how unique or loud a specific data comment is, its mathematical gradient, meaning its influence on the model's learning, is literally clipped to a maximum threshold.
So it physically prevents any one document from screaming over the rest of the crowd and getting stuck in the model's memory?
Exactly. No one gets a megaphone.
And then comes the second part, the noise.
Right. After clipping the influence of all those individual examples so they're at the exact same volume, the system aggregates them together and adds properly calibrated Gaussian noise to the gradients.
Continuing our stadium analogy, that's like what?
It's like pumping a layer of white noise or static through the stadium speakers.
Like, no.
The model can still clearly hear the overall tune the entire crowd is singing. It learns the general knowledge, the grammar, the facts.
But it can't hear the individuals.
Right. It becomes mathematically impossible to pick out any individual person's specific voice through the static.
And the research doesn't just say we added some noise and hoped for the best. They actually quantify this with a specific privacy guarantee, right?
They do. And this is a vital point for anyone who cares about data security. VaultGemma provides a strict, sequence-level privacy guarantee.
What are the numbers?
Specifically, the paper notes it achieved an epsilon of less than or equal to 2.0.
Okay.
And a delta of less than or equal to 1.1 times 10 to the negative 10.
Okay, let's translate that for a second. What do those numbers actually mean in practice?
Well, epsilon is essentially the measure of privacy loss. An epsilon of 2.0 is considered a very robust, tight bound in the world of differential privacy.
It caps the leakage.
Right. It means the maximum amount of information the model can leak about any single training document is strictly capped. Delta, on the other hand, represents the probability that this privacy guarantee might fail.
And they have delta at 1.1 times 10 to the negative 10. That is an absurdly small number.
It's microscopic. We're talking about a probability of failure on the scale of roughly 1 in 10 billion.
1 in 10 billion.
Yeah. Together, these numbers provide a provable, ironclad mathematical bound against information leakage.
Think about your own data floating around the web for a second, an old blog post you wrote, a forum comment from 10 years ago.
Maybe a snippet of code you uploaded to a public repository.
Right. How much better would you feel knowing a mathematical formula guarantees your specific information literally cannot be regurgitated by an AI?
It's a huge relief.
What stands out to you about that? Because for me, it's the profound shift from having to trust a tech company's word or their filtering algorithms to trusting a verifiable mathematical proof.
It completely shifts the paradigm of trust in artificial intelligence. You no longer have to blindly trust the corporation. You can trust the math.
But I imagine implementing that rigorous math at a scale of 13 trillion tokens requires an entirely different approach.
It changes everything about how we build and compute these models. Honestly, it is an engineering nightmare.
Here's where it gets really interesting, the compute challenge.
Oh, yeah.
We all know training a standard LM is notoriously expensive and computationally heavy. But adding differential privacy at the pre-training stage seems to make it exponentially harder.
Exponentially is the right word.
The paper mentions they had to fire up a massive infrastructure, a setup of 2048 TPU v6e chips running for 100,000 iterations.
The scale of the hardware is staggering, but raw compute power wasn't enough to solve the problem.
Really?
No, they had to make highly specific, clever architectural tweaks to the model itself just to accommodate the DP training.
And this ties perfectly back to our stadium analogy, doesn't it?
How so?
Well, if you are pumping static over the crowd so you can't hear individuals, you need a massive crowd shouting the same tune just so the model can hear the underlying melody through the noise.
That is exactly the issue. Because DPSTD calculates and clips gradients and then adds that Gaussian noise, having a massive batch size is an absolute necessity.
You can't just train on a few documents at a time.
If you only look at a few examples at a time, the noise overwhelms the signal, and the model learns nothing. It just gets confused by the static.
So what batch size did they need?
They needed a jaw-dropping expected batch size of nearly 518,000 examples per step.
500,000 examples at once.
Yes.
But fitting 500,000 text examples into the memory of those TPUs all at the same time is practically impossible with standard model architectures. How did they force it to fit?
They had to get creative. First, they dropped the sequence length.
Which is the amount of text the model looks at in one single chunk.
Exactly. They dropped it down to 10 under 24 tokens. By shrinking the sequence length, they drastically reduced the memory and compute requirements per individual example.
Allowing them to pack more examples into the batch.
Right.
But changing the sequence length ripples through the rest of the design, right?
It does. Because the sequence length was smaller, they opted to use global attention on all layers of the transformer.
Rather than the sliding window attention you might see in other standard models.
Exactly. Furthermore, to stabilize this massive, incredibly noisy training process, they used a technique called pre-norm with RMS norm on the inputs of the transformer sublayers.
Okay, let's pause on that. Why do they need RMS norm? What does that actually do?
Think of it like shock absorbers on a car.
Shock absorbers?
Yeah. When you inject that much mathematical static into the system to protect privacy, the model's learning process can easily become jagged, chaotic, and spiral out of control.
Bouncing all over the road.
Right. RMS norm essentially acts as a stabilizer, anchoring the mathematical updates and keeping the model's learning trajectory smooth despite the constant noise.
That makes perfect sense.
Right.
So they shrink the text chunks, use global attention, and add shock absorbers to handle the noise. Also, they can process 518,000 examples at a time.
Exactly.
But gathering a batch that large introduces its own logistical nightmare. How do you even feed the beast that fast?
You've hit on a massive historical bottleneck in privacy research.
Really?
Oh, yeah. To build these massive batches efficiently, they used a statistical technique called truncated Poisson subsampling.
Okay, what is that?
Normally, Poisson subsampling includes each example in a dataset with a fixed probability, which results in batches that vary in size.
Sometimes you get 500,000, sometimes 520,000.
Right. And variable batch sizes are terrible for training throughput on highly synchronized hardware like TPUs.
So the truncated part means they force the batch to be a fixed exact size every single time.
Precisely. If the batch randomly happens to be too small, they pad it out with empty data. If it's too large, they truncate it and cut it off.
Got it.
Now, earlier research in this field suggested that to maintain the strict mathematical privacy guarantees, you had to do all this complex data sampling as a pre-computation step.
Meaning you'd have to use heavy data processing tools like MapReduce to sort and sample all 13 trillion tokens before the actual AI training even started.
Yes.
That sounds like a massive headache for data storage.
A huge headache and incredibly slow.
Mm-hmm.
But the VaultGemma team realized they didn't need to do that. They implemented this truncated Poisson subsampling directly inside their data loading pipeline.
On the fly.
On the fly, using a specialized tool called PyGrain. It acts like a real-time conveyor belt.
That's brilliant.
As the data is being fed to the supercomputers, it is being perfectly sampled and batched in real time. And the overhead was astonishingly tiny.
How tiny?
They found that at these massive batch sizes, the empty padding accounted for less than 2% of the total batch size.
Less than 2%. That is incredibly elegant engineering.
It really is.
It eliminates the data sorting bottleneck and keeps the information flowing fast. But even with the data flowing perfectly, I have to wonder how they knew what settings to use.
Okay.
Well, with standard models, researchers have a pretty good feel for scaling laws. They know how to tweak the learning rate and the training time based on the size of the model. Did they just use standard AI scaling laws?
What's fascinating here is that the introduction of differential privacy completely disrupts those traditional scaling laws.
It throws them out the window.
Completely. The noise fundamentally changes how the model learns. So the team literally had to invent new scaling laws specifically for differentially private language models.
Wait, so they couldn't just guess the optimal learning rate?
Guessing is far too expensive when you are renting thousands of TPUs.
Fair point.
Instead, for each experimental configuration, they ran 7 completely different training runs, each with a slightly different learning rate. They then took the final loss values, which is a measure of how much the model is struggling from those 7 runs, and plotted them on a graph.
And because the relationship between the learning rate and the final loss is convex, it forms a parabola on the graph.
Exactly. They mathematically fit a quadratic function to those 7 points, and the absolute lowest point of that parabola, the vertex, gave them a highly accurate mathematical estimate of the perfect learning rate.
No guesswork required.
None. But they also needed to predict the loss over continuous training iterations to know how long to train it.
Right, because you want to know how smart the model's going to get if you run it for 50,000 steps versus 100,000 steps.
Without actually having to spend millions of dollars to run it all the way to the end just to find out.
Exactly. So how did they solve that?
To solve that, they used parametric extrapolation. They ran 5 separate, shorter training runs, recorded the loss for each, and fit a specific mathematical formula to those points,
Allowing them to seamlessly interpolate and extrapolate the expected intelligence of the model.
Yes. In fact, their new scaling law predictions were so accurate that after the full 100,000 iteration training run of VaultGemma 1B, the actual final loss was within 1% of what their newly invented math predicted it would be.
That is the definition of precision engineering. I am genuinely in awe of the sheer scale and cost required to figure this out.
It's a massive achievement.
So we have the massive compute, the clever architecture with shock absorbers, the real-time conveyor belt batching, and these newly minted DP scaling laws. It all culminated in VaultGemma 1B.
It did.
So what does this all mean? Did all this mind-bending math actually work? Did they successfully build a model that doesn't memorize?
To prove it, they put VaultGemma through a rigorous, large-scale memorization test. And the methodology here is key. They didn't just ask in a few tricky questions.
What did they do?
They took 1 million training data samples, distributed uniformly across the different data sets the model had seen during its creation.
1 million samples. Okay, how does the test actually work mechanically?
They feed the model a 50-token prefix directly from the actual training data. Basically, they give it the first 50 words of a real document.
Imagine feeding the AI the first 50 words of a private medical record that somehow got swept up in a scrape.
Exactly. Then, they ask the model to generate the next 50 tokens. They are fundamentally testing to see if the model can perfectly autocomplete a private document it saw during training.
The ultimate high-stakes fill-in-the-blank test.
Yes. If all 50 generated tokens match the original source perfectly, it is flagged as exactly memorized.
And what if it's just close?
If the generation matches the source up to a 10% edit distance, meaning it got mostly everything right with just a few minor typos or substituted synonyms, it is flagged as approximately memorized.
And what were the results? because looking at the earlier data, even the advanced non-private Gemma 2 and Gemma 3 models had detectable levels of memorization on this exact same test.
The results for VaultGemma 1B were absolute. Across the 1 million samples, VaultGemma 1B showed exactly 0% exact memorization and 0% approximate memorization. No memorization was detected whatsoever.
0%. That is incredible. A total and complete success for the privacy guarantees. The mathematical bounds held up perfectly in empirical testing.
It is a remarkable achievement. However, this raises an important question.
Which is?
If a model is this heavily restricted, if its gradients are clipped and noisy, and it has shock absorbers just to function, how smart is it actually? We have to address what researchers call the utility gap.
Right, the sobering reality check. We can't have magic.
No, we can't.
If you scramble the data with that much static to protect privacy, the model has to work infinitely harder to learn basic logic and reasoning. How does VaultGemma 1B perform on standard intelligence tests compared to normal, non-private models?
The researchers ran VaultGemma across standard academic benchmarks. Tests like ARC for reasoning, LLM for common sense inference, and BullQ for reading comprehension.
And the results?
When compared to the non-private Gemma 3.1b model, there is a distinct, measurable drop in performance. For instance, VaultGemma 1b scores 26.45 on the ARC challenge, while the standard Gemma 3 scores 38.31.
That's a noticeable gap.
On BullQ, VaultGemma hits 62.04 compared to 68.75.
So it is noticeably less capable than its state-of-the-art non-private sibling.
Yes, the utility gap is real. To put it in broader historical perspective, the researchers compared VaultGemma 1b to an older 1.5 billion parameter GPT-2 model.
Wow, GPT-2. That model is roughly 5 years old at this point. That feels like ancient history in AI time.
It does. But VaultGemma 1b and the 1.5 billion parameter GPT-2 model perform very similarly across these benchmarks.
Okay.
It illustrates that today's differentially private training methods produce models with utility comparable to non-private models from about half a decade ago.
But, bringing this back to you, the listener, while matching a 5-year-old model might initially sound like a step backward in raw intelligence, it is actually a monumental leap forward for safe, responsible AI.
It absolutely is.
Think about it. We now have a model that can reason at a highly functional GPT-2 level, but with absolute mathematically proven guarantees that it will not leak the personal data it was trained on. Achieving that level of intelligence through that much mathematical static is a miracle of engineering.
And that is a vital takeaway from this paper. Google is not releasing VaultGemma 1b claiming it is the smartest reasoning model in the world.
No.
They are releasing it entirely open weight, along with their precise methodology, their pi-grain data loaders, and their new scaling laws, to give the global research community a foundational baseline.
They are essentially handing the global community the blueprint and saying, we proved it can be done securely, now let's work together to systematically close that utility gap.
Yes, it radically lowers the barrier to entry for everyone trying to build privacy-preserving technology.
It's an open invitation.
By open sourcing the weights, it also provides an immediate out-of-the-box tool for applications where the privacy of the training data is absolutely paramount. It proves that the gap between privacy and utility is not an insurmountable wall. It is merely an engineering challenge that we now have the structural tools to measure, iterate on, and improve.
To summarize what we've unpacked today, VaultGemma proves that we do not have to choose between having powerful, open-weight AI models and protecting the privacy of the billions of data points they learn from.
We can have both.
The superficial band-aid of fine-tuning privacy is no longer our only option. We can build privacy deep into the foundation, mathematically bounding the influence of any single voice in the crowd, and still produce a highly functional general-purpose language model.
Exactly.
But as we wrap up this deep dive, I want to leave you with a final lingering thought to mull over, something that builds on everything we've discussed today about the nature of memorization.
Let's hear it.
If VaultGemma proves we can mathematically guarantee a model forgets the individual secrets, private documents, or specific phrases it reads during training, how might this completely change the legal battles around copyright infringement and data ownership in AI training moving forward?
That is a fascinating angle.
Right. If the AI mathematically cannot copy your specific work, who truly owns what it creates?
A cushion for the courts, probably.
Definitely. Thank you so much for joining us on this custom deep dive. We hope it brought you some valuable aha moments, and we wish you the absolute best on your continued learning journey.